Hi guys, till now we have studied here. We have seen the computational architecture of a finite state machine. This is the compute. Sorry, just wait. Okay. This is actually we have seen in our previous lecture. We have seen the concept till here. Now we are now look at the our next concept. What it is? Okay, just wait. What? Okay, just normal view. Okay, till now we have studied here. Now look at the next part. Next concept, what it is. Okay, this is a full page view. Okay, now look at this point. Finite control stores only current state. It does not know anything about from which state transition start and how it is proceed further up to the current state. I have already told you, whatever we have a finite memory like this, whatever we have finite memory like this, it will store all, it know about the current state only. It does not know where our transition is started like this and how this transition, suppose if we reach this q2, sorry, now suppose if we reach this to q2 state, however this transition is reached there. This thing does not know this finite control machine. This finite state machine is actually less powerful than the computer, because I have already told you that computer is based on the Turing machine. We will see in our later lectures, in later topics, whatever we learn here. This is a Turing machine. Our actually today's computer is based on the Turing machine. Our today computer is based on this Turing machine. Okay, so now let move to the our next topic. What it is? It is a language of a finite automata with examples. So now look at the what are the languages of a finite automata. We see the example one by one. Now look at here. There is a, this is a W. This is a word or a string, belongs to sigma star. What it is? It is actually a clean closure. What we this term is named as clean closure or a universal language. Clean closure. What it is? It is a clean closure. So W is excited by finite automata. Now look at the part what it is saying here. Now look at this, where suppose we have a string consists of these three actually these three symbols, s0, s1, s2. We starting with the initial state. So on reading the s0 symbol, or this is a symbol for an input alphabet, s0, we will move to the next state. Then again then on reading s1 we will move to the q2 state. It is our final state. On moving s2 we will remain in the same state. On reading, this is actually, this is one is a n, this is one as an input symbol. What it is? This one is like an, this one is like an, this one is like an input symbol. So now look at our, move to the now look at the example here. What it is? Now we have given a finite automata in this example. What it is now? Sorry, in this example we have given a finite automata. We have to determine what are the language accepted by this automata and also find the words from the okay, what are the language accepted by this finite automata? We have to find, now look at here, we have to find what are the language and what are the string this language contains. There these languages, these languages consist of so many words or strings. We have to also determine what are the words here by looking at this example. Okay, Now look at here. Okay, let me zoom here. So now look at here. There is actually how we will determine it. Now look at the how we are reaching to the final state. Now look at this part. On getting the transition B, first now look at only those transition which are getting to us to our final state. This is our final state of this question. What it is? It is our final state of this question. So now look at this. On reading the symbol B, we will on reading this B symbol, we will move to the Q1 state. On reading an A symbol, we will move to the this Q2 state. So what are the words is containing in this language? First words we will find it. What it is? It is a B. It is a B A. Then if we will get the any symbol A, so it will remain in the same state. Now look at here. If we will the symbol B, it will remain in the same state here. Then if we will get any symbol B, then we will go to the state Q1. What it means? Any words. What are the language? Now look at this part. If we like this BA, if we like a word like this, BA is accepted. Suppose we have another words is A, B, A, B, A. It is also accepted by this machine, because now look at this. Just let me change the pen color so you will not get confused. Now look at this. On reading this B symbol, we will reach to the Q1 state. On reading this A symbol, we will move to the our Q2 states. And on reading this A symbol again, we will then move to the Q0 state. Where will we move? We will move to the Q0 state. It is actually a Q2. So on reading these B symbols, we again move to the Q1 state, and on reading these B A symbols, we will move to the Q2 state. What it means? Any string that is ending with BA will accept by this machine, by these finite automata or a finite state machines. So what will be our language? Now look at here. Just let me scroll down it. Okay. What will be our languages? Languages consists for the language for this machine. What are the words included in this language? It will be BA. Okay. Now look at this part. How we will define it actually? Okay. Now look at this part. W. Okay. Now look at this part. Words is belongs to sigma star universal language, such that this is the symbol for such that W is equal to XAB. What it is? It is a XAB, where X belongs to sigma star, because sigma star contain, even it can be an epsilon, but what will be our string? It will be ending with BA. Okay. So this node will be AB. Just let me erase here. I have write it by mistake. Okay. Now this node will be AB. This will be X of X and BA. Every string ending with BA is accepted by this language. Is accepted by this machine. So our language will be like this, where our input alphabet is sigma is equals to AB. It should be end with BA, not a AB. Okay. If you have any doubt in this, you can ask me in the comment section. Okay. Now moving to our next page. Okay. Now look at this example. This is the second example. We have to just change me the Okay, change the pen color. Now look at this example. We have to find its language. So how we are going to find out now? First we will look the simple transition which will get to us to the final state. This is the final state. This is the okay. This is the final state for this machine. Now look at this transition. This is an A. On reading A symbol, we will transit from the Q0 to Q1. This is Q1, and on reading A symbol again, we can move to the transition Q2. So what our first word of this language will be? It will be like this: A, A, double A. So our first will be accepted like this. Then we can get any number of A's. We will remain in the same state. What this same state is as final state. So any number of A greater than the 2A, we will remain in the same state. This word is also accepted. Now look at this part. If we get a B, then we will move here. If we get a B on a Q2 transition, suppose we have a words like this: A, and B, then what will happen? We will move from to Q to the Q0 transition. Then again we require 2 A's. Again we get a 1A, then we will reach to this Q1 state. If we get a one more A, then we will reach to our final state. So there should be actually a total. Okay. Actually there is ending must be with the double A. This is the this is the language which is ending with the double A. There should be at least 2 A's. Now look at this example. This is also ending with a BA. If I will ignore this A, then this string is not accepted by this machine. So we can say the language. So the language of this language. What is the language of this machine? Of this machine is like such that there is a word is equals to x double A. Actually it is ending with the double A such that where x belongs to sigma star. X can be anything. It can be also an empty string also. So this is the best representation in a mathematical form, in very clear and crisp form. We have a word. It will accept all the words x double A such that x belongs to sigma star. Where what is our input alphabet? It is only 2 actually. That is A and B. That is A and B. We have only 2 input alphabets here. We have only two input alphabets here. Now moving to our next example, we have to find its language. This state diagram is given here for the finite state machine. We have to find its language. What its language now? Look at this part. What the first word it will accept? It will accept if we get a transition of a, then we will reach to our final state. If we get any number of A's, we will remain in the same state. It can be any number of A's. Now look at, if we will get a B, then we will go to as our initial state, which is Q0. So suppose if we have a string like this AB, then we will go to our Q0 state. It means this string is not accepting by this machine. So now look at so what is the language of this machine? The language of this machine would be like this, x of A. Actually there is at least one A should be there. X of, actually, okay, just let me properly here. What the strings present in this machine will be like such that x concatenated with A such that x belongs to sigma star, where x can be, x belongs to x belongs to sigma star. X belongs to sigma star. So this is the example for this language. Now just move to our next example. We can also say this machine accepts those languages only which contains one or a more s. At least one s should be there. So now look at our example number 4. What it is? This machine simply it is accepting the words which is B, and then again if after B A comes, it is also accepting this word. Just let me write here properly. It is also accepting this word. But if there is a double B's, if there is two B's, then this machine is not accepting, because on first B we will move to this transition. On the first B, on the second B we will move from Q1 to Q0. Q0 is not our final state, as we can see here in the given question. So double B, so this double B is not accepting here. What it means? So how we will recognize this language? This language is like such that, okay, BA. Now look at one more example, one more string words. Suppose there it will be B, A, B and B. Okay. Now look at this example. There will be like B. If we get A, then we again get a B. Then we again get a B. Then we will move to the, then this string is accepted by this machine, because from B we to go to Q1, then we go Q0, then sorry, from Q1 we will remain in the same state. Then from here, from Q1 we will move to the Q0 state, and then again on getting this last B we will move to the Q1 state. So this word is also accepting. What it means here, any string, this is accepting all the words which is ending with B, which is, okay, now look at okay, which is containing odd number of B's here. Actually it is accepting those language only containing odd number of B's. Actually there is one B, so it is accepted. There is again one B, so it is again accepted. If there is two number of B's or a four number of B's, then it will not accept that word. Now look at this. If we have a one B, we will move to this state. What will be number of A? It does not affect, it does not matter here. When we get the two B's, then we will move to this state. Then we will get, if we increase the one more B's, then it will be odd number and it is accepting by this machine. If we get one B, if we get B one more time, then it will move us to this Q0 state. So containing odd number of B's. What it is? Containing odd number of B's. Odd number of B's. So how we can represent it like this? There is a language W is equal to X such that X belongs to sigma star and containing odd number of B's. We have specified here the constraint what this machine has put up here. So X belongs to sigma star. It will be a subset of this universal language and containing odd number of B's here. Okay. Now move to the next page. Okay, now look at here. This is the example number 5. We have also determined what is the language accepted by this machine. Now look at its first word here. It is actually accepting. Now look at the first word. What is it? Is on getting A. If we getting A B, then we will move into our final state. Okay, On getting AB, we will moving to our final state. Then after AB, any number of A's or any number of B's we are getting, we remain in the same state, which is also a final state. It can be here any number of A's or any combination of B's here. It is also accepted by this machine. So actually okay, now look at the PM. Okay, now look at here what this machine says. It will accept all these string. It will accept all these string which contain AB as a substring. This sequence is also important in substring concept because AB should be there. If there, because B is not accepting here, this sequence is very important. Now look at, if we get a B, we will remain in the Q node. If we get a, then we will read the symbol A node, our tape header. Then it will move to the then it will move us to the Q1 state. Not, and Q1 is not our final state. So AB should be there as their substring. So this is for this machine. Now look at, okay, we can also write like this. W is equals to X such that X belongs to sigma star in which A followed by B's. In which A followed by B's. We can also write like this. Now there is also a concept called unreachable state. What it is? Now look at here. This view. I have to zoom it. Okay. Now look at the concept of the unreachable states. What it is now? There is a language. It is a language. It is an empty language. Empty. I have already told you. Empty language even does not contain an empty string. Not contain epsilon. This empty languages does not contain even empty string. This language does not contain even empty strings. So this is the now look at the first example here. What it is? It is like this is our initial state. Actually this is the starting. This point show this we are starting from here. This is our start state. We are starting from here. So as we are starting from here, it contains epsilon transition also here. If we get any number of A's, B's, we will remain in the same state. As we will get, actually now look at this. There is no option from this. There is no way from which we can reach from where we can reach to our Q1, because Q1 is a final state. So this machine is without a final state. So this state is called as a unreachable state because we can't reach here through any transition or with the help of any transition. Now look at the second example also. This is also similar like this. We cannot reach here Q1 as there is no transition from here to here exist like this. There should be direction from Q0 to Q1, not from Q1 to Q0. So now moving to our third example. What it is? It is a okay. This is our third example. It is a initial state. What it is? It is our initial state, or we can also say it is a start state. We can now look at this. There is no final state here. So this is also a unreachable state and also having no final state. In this we have the final state, but in this case we have not any final state. So now look at this example also. What are the language represented by this machine? Actually this is showing this is also accept epsilon because this is our initial state and a final state as well. This is our both. This is our initial and this is our initial and final state also. So it will accept only epsilon string because no input alphabet is given here. So it will accept only epsilon empty string. Now look at this example. What are the language it is accepted by this? This will accept an empty string and then any number of a's should be there. Any number of any number of a, just wait, okay. Then it will contain any number of a's there. So how we will represent it properly? Now look at here. There's a language such like that 0 to the power n, 0 to the power, and this is an example of, actually this is an example of an infinite language, because we can also construct a finite automata for it, but this language is not a finite because length of this language is not finite. How we will define it? There will be a 0 to the power n such that where n is greater than n equal to 0, where n is greater than n equal to 0. So it will also contain an empty string 0 to the power 0, it will be an empty string 0 to the power 1, it will be a 0, and any numbers of 0 this machine can contain. Okay, now moving to our next page. Okay, now look at here. I've already told you about it. Where it is? Where is my cursor? Okay, now look at here. I have already told you about it. So this is language is equal to universal language. We can also say it is a universal language because there is only one input alphabet and it is containing all the string, because sigma star contain all the string formed using, and also contain an empty string, and also contain all the string formed using input alphabet in any order. So now look at this example. What it is? It is, here we have a Q0 as our initial state and a Q1. Here actually there is no final state. So what is this language is accepted by this machine? This is a null language. So we can also send empty language actually. This is the representation for a null set. So an empty language accepted by this machine. Now look at this example. We can't reach this unreachable state, so this is also the language which will accept it. It will be also an null language. Null language means it is an empty language. Okay, now move this. Look at this part. Okay, AB. Now look at this part. What are the language accepted by this? It will accept all the language containing epsilon a, b, or any number of a, b in any order or any concatenation order. It means b can be first here any number of times, and a can be, or a b can be in the middle in any order it any number of times, such like that. It will also representing a universal language. Actually it is a clean closure if we look at it carefully. So this is an example for the second one. What it is now? Now look at here. What are the language accepted by this? What are the language accepted by this? It will contain an epsilon language. It will contain an epsilon language. Then there is a transaction on a B. It will containing all the languages. Actually now look at this. This is the minimal DFA. Minimal DFA means, just I have to change my pen color. What is minimal DFA means? Minimum number of states should be there. I have already told you, for a single given languages there are many state machine are possible, but this is a minimal DFA with minimum number of states. Minimum number of states. Minimum number of states. So this is only one state and accepting this language, representing this language like this. What is here? Here our input alphabet is A and B. What it is? It is here our input alphabet is A and a B. So this is the same thing with the 2 state, and this is the same thing with the 3 state if you look it carefully. So this is not a minimal DFA. Minimal DFA only this is over this input alphabet, which is A and B. Okay, now moving to our next example. Okay, now there is some points what it said, for example, and we can conclude. Actually, we can conclude from example 9 following points. A sample language L can have multiple DFA. Actually, a same language. What it is now? It is a word which is a same language L can have multiple DFAs. Minimal DFA means minimum number of states should be there. Now look at this example. What are the language containing this? This is also containing all that languages, but this is with the unreachable states. This is also the same thing, but not with the minimal number of DFA. Now look at this. Every DFA accept only one language. No single DFA can accept more than one languages. Multiple DFA that accept languages all words in L. What? Now look at this point carefully. Only suppose there is deterministic finite automata. We have a machine. It can accept only one language at a time. A language, it can accept only one language at a time. It cannot accept. Suppose we have a given state of machine and it is accepting more than one languages at a time. It cannot accept more than one languages at a time. So now moving to our next example, what it is now. So minimal DFA means minimum number of state. Minimum DFA exactly one that accepts all the words belongs to language. What it is written here, this is the all the words what it is written here, this is a all the words belongs to L. All the words belongs to L. So now okay, just wait here. Okay, now moving over to the next topic, which is a construction of finite automata for a finite languages. We will see how we will construct an finite automata if a language is given like this. So okay, now look at here. Actually, suppose we have given language like this, L is equals to double A. So how we will construct it? A state diagram for it. Suppose there will be always a initial state which we will name as a Q naught here. So on getting an input symbol A, we will moving to the next state which is as a Q1. On getting an input symbol one more A, then we will reaching to the our final state which named as a Q2 here. So now look at this. Here we have an input alphabet in the language only A symbol. We have only one symbol here in the input alphabet languages. So this is our finite state machine for the given languages. If we get one more A, suppose where it is, our machine should define all the transition. If we get one more A, then this machine will not accept this word and we will reach to the dead state. Dead state means this will be a next state like Q3. On getting any number of A's, we will remain in the same state. Dead state means where we cannot reach from this state. Actually, we cannot reach from this state to the final state. So this is also, this is called a dead state. What it is? What it is? It is a, it this state is named a dead state, from where we cannot reach to the final state. Dead state is that state from where we cannot reach to this final state. It means, I just to show you pictorially, we cannot reach final state from the dead state on any transition. This is the concept of the dead state. Now actually, now look at this formal definition. There is no way to come out of the state, is known as a dead state. Okay, just wait for 10 seconds. Thanks for waiting. Now continue it. Move to the next page. Okay, now look at this example. This is the language is given here, which is L is equals to, just wait, what we have seen till now. We have seen only one example here. Very second example. Okay, just leave the number. Now focus on the core concept. Now look at here. This is the language is given to us and AB. How we are going to draw its finite automata. Now look at here. This will be our initial state, which is Q naught. On moving A, it is accepting a word called A. So on seeing this input symbol, we will transit from state Q0 to Q1. Then this is also our final state. This is also our final state. Okay, let me draw here it in the bigger form. Okay, now look at here. This is Q naught. On getting an input symbol A, we will move to this next state. There is also a word called AB. If we get a B symbol, then we will move to the next state, which is as a Q2. Which is as a Q2. It will accepting only two these languages. What happen if we will get this will be, we will name as a Q3 or a, so on getting any A or a B after it, if we get a, suppose if we get a word like this AB, then there will be any A, any number of A or a B, then we will move to the, we'll just write put here A and a B. On getting any A or a B, we will move to this state, and this is our dead state. I am writing here just in short form, it is a DS. DS means it is our dead state, from where we cannot reach to the final state. So on getting any transition after this, we will remain to this state. We will remain to in the same state, which is a dead state. So we have defined on a input symbol A, we have to define all the input. We have to define all the transition for a single state. We have defined only for A. On getting A, we are moving to the Q1. What if we will get a B as our, suppose we get a B as our substring, B as a word. So what it will be, it will not accept this language and will move to the our dead state, where we cannot, from where we cannot reach to our final states. So we have defined for this state, we have defined on that, we have defined for the transition B, we have not defined of a transition A. On getting a transition A, this will also move to this dead state. this will also move to a dead state. So for this state, two transition is defined here, A and B. For this state also two transition defined here, A and B. And for this state, A and B transition is defined. And for the dead state, the AB transition is also defined. So now look at this point is very important. So that or we have to define all the transition. We have to define all the input alphabets for a single states in every our DFA. So therefore it is called as a deterministic finite automata. Just let me write here what it is now. DFA means deterministic finite automata. We can also say it is a finite automata or a finite state machine. Now look at the third example. What it is? It is saying we have to accept only these languages, AB and BA. Only these two words. How we will going to design it? Now look at here. Our first simple thing is to design. We have to design according to the given words here. So on getting A, we will move to the state Q1. We cannot put two input symbols and move to the one transition. This is not possible in this deterministic finite automata. So now look at here. On getting A, we will transit from Q0 to Q1. On reading this input symbol B, we are getting transition from Q0 to Q1 and Q1 from Q1 to Q2. Similarly, so this will be our final state. What is? It will be our final state. Now look at here. On getting B, we are moving to the next state. Okay, let me scroll down here. We are moving to the next state. What is it? It is a Q3. On getting A, on reading this input symbol A, we are moving to this Q4 state, which is also our final state. So in this case, we have two final state instead of a one, because words are given such like that in this question. So here we will accept this, but we have not defined for the all the inputs here. Now look at here. We will also first we will define for the given languages. First we will define for the given words, and then we will define for the words which is not given in the languages in this type of questions. So now look at here. This is a Q0. Okay, these two transitions defined for it. For these two transitions not defined here. So now on getting B, we will move to the another state which will named as a Q5. It can be also a dead state. After getting any number of A's, okay. Now look at here. This is not our dead state. Now look at here. On the B, okay, just wait here. Now look at here what it will be. Okay, on getting B, if we get a B from a Q1, then we will move to this state. So that if we will get any A, then we will move to the next state. So transition is also defined for this state. A and B. This is B. Sorry, my bad. Okay, now look at here. This is not will be B. Sorry. Now look at here. So for B we have defined already. We have to define for A. What if we will get one more A? If we will get one more A, then we will move to the state called, we will named it as a Q5. So we have defined for the two input alphabets here. Similarly, we will define for it. After AB, what will happen if we will get any A or a B? If we get any A or a B, then we will move to this state. If we get any A or a B, we will move to this state. What will happen if we will get B here, if we will get B here, double B, then we will move to this dead state. What will happen after BA? We will get any number of A or a B. We will move to this state. So we have defined for all the state except the Q5 state. For Q5 state, now let me change the pen color so you will not get confused. For the Q5 state, it will remain in the same state on reading the symbol AB. So for these languages, we have defined all the state. So now look at the symbols. We have an input alphabet which is given in the question here. Total how many states we have here? Total 6 states we have here: Q0, Q1, Q2, Q3, Q4, Q5. And how many final states we have here? We have only one final state in this case, while in our previous case we have two final states here. In this case we have in this case we have two final states here, but in this example we have only one final state here. And there is an input alphabet, there is a transition we can simply define like this: Q. On getting any input alphabet, it will move to the next state. And there is also fifth. Actually, the DFA is a collection of the 5 tuple. DFA means deterministic finite automata. So we have defined all these 5 things here. So now look at our this example, which is here. Okay. Okay, now look at this example. First, I will suggest you to try it at home. This is your homework. Try to design a finite state machine for it. Construct for this given language. Construct a finite automata for it. Construct a finite automata for this. This is your homework. So I am ending my lecture here. In the next lecture we will see from this 6th example. This is your homework. So you can check. You should try it by your own. Thanks guys for watching this video. If you find this video is really helpful for you for your get preparation exam and a semester or an entrance exam, then like it and share it with your friends. Thank you guys one more time.